you ever noticed that when you step into an elevator, sometimes it feels like there's an unseen force pushing down on you or pulling up on you? In fact, if you were to stand on a scale in an elevator, you might notice that the scale reading, or your weight, might change. Why do you think that happens? Well, whenever we're feeling a force being exerted on us, that means that there must be some sort of acceleration going on. So the elevator must be accelerating if our net force is changing, which is causing the scale reading to change. In fact, there could be a way that the elevator could be accelerating so much that we almost appear weightless, like this puppy right here. So let's talk about this. Let's break it down. The mass of the person is constant, so their weight force is going to be constant too, meaning that it won't change. We're going to say that the normal force is the force of the scale pushing up on you. This is what we're going to call the scale reading. Net force and acceleration always point in the same direction, and we're going to label our coordinates as up being positive and down being negative. So let's take a look at case 1. No acceleration. That means acceleration equals 0. This can occur if the object is at rest or if it's moving with constant velocity, aka equilibrium. So we know that since the person has mass, they must have a weight force represented by this red arrow. In order for the object to have 0 acceleration, there must be no net force. Therefore, the force of the normal force must equal the weight force. So our scale reading would be exactly what we would expect it to be. So let's look at case 2. We're traveling up and speeding up. So what direction would our acceleration be pointing? If you said positive, you're totally right. So the acceleration is positive, so the net force must also be positive because they always point in the same direction. So that means my normal force would be much greater than my weight force. So it's going to feel like I weigh more or that I'm pushing down into it. So in this case, the scale reading will be greater than our actual weight. What about case 3, traveling up and slowing down? So if I'm traveling up but slowing down, that means my acceleration needs to point in the opposite direction of my motion. So my acceleration in this case is going to be negative. So that means that my net force must also be negative. So therefore, the scale is not going to push up as hard as it would up against me. So in this case, my scale reading would be less than my actual weight. Case 3, or really case 4, traveling down and speeding up. So if I'm traveling down and speeding up, my acceleration would have to be negative because down is a negative direction, and if I'm speeding up, my acceleration points in the direction of motion. So then my net force must also be negative. So what does that mean for my scale reading? Well, it's got to be less than my actual weight to give me that negative net force. Case 4, traveling down and slowing down. If I'm traveling downwards and slowing down, that means my acceleration is going to point in the opposite direction of motion, so it's going to be positive, and therefore my net force must also be positive. So what does that mean for the scale reading? Well, it's going to be much greater than my actual weight. So the scale would read something greater than my actual weight. Now, what if I'm in free fall? Free fall means that your acceleration equals negative acceleration due to gravity, so negative 9.8. If that's the case, then that means my net force needs to equal the weight of me, or of the object in there. So if that's the case, if my net force equals the weight, then that means I'm going to have no normal force pushing up on me. Because if I had any normal force, then my net force wouldn't equal my weight. So I'd be registering as weightless. In fact, this is how we simulate weightlessness by taking people up really high and then just literally dropping them. If you've ever gone into the Tower of Terror at Disney, you've experienced weightlessness.